today. We have three talks, and the first one is by Erin Zimmer, who's a developer, a member of the Melbourne community of developers. She's an experienced speaker about many languages, some of which you may know and some of which you may not know, and not Python. So here she is, Erin Zimmer, with Anatomy of a Browser.
Hi. So yeah, today we are going to look at what's going on inside a browser when it parses your HTML. And I really don't know anything about Python, so that should be fun. Like Javier said, my name's Erin. I am a Mozilla tech speaker, and I'm a Google developer expert in the area of web. So I have seen a browser or two. I work for a company called Shine Solutions. We're a consultancy here in Sydney and down in Melbourne. I'm not sure that we do any Python, actually, but we're always looking for web developers if anyone out there is looking for any work. Most importantly today is my birthday, so... No. Thank you. Yep.
What's your mother's maiden name?
So if any of you have ever developed for browsers, you're probably aware that there's a bunch of them. And it can be a little bit tricky to get your stuff to work the same across all of them. The good news is, though, it's actually a lot easier now than it used to be. So back in the bad old days of the browser wars, when everyone was using Netscape or IE, you basically had to choose whether your app was going to work in one or the other. Whereas these days, it's a lot easier to make things work across all browsers. And there's a couple of reasons for that. So the first one is that we have all of these wonderful standards organizations. We've got the WhatWG, who I think have the best logo. It's the little question mark. The World Wide Web Consortium, and the amazingly named Technical Committee 39. It's quite obvious what they do, right? Yeah. So they take care of the JavaScript spec. These organizations have been around since the 90s, but these days browsers actually listen to them. So the good news here is that while all browsers don't have all features, like something might be implemented in one browser but not another, if you have a feature that's been implemented in two browsers, chances are it's been implemented to the same specification and it's going to work the same. So this makes life a lot easier. The other thing that makes life easier is actually the way that browsers are built. So if we look at a standards compliant browser here, we can think of it as having two parts. So the first part is this bit. And this is the part of the browser that's not responsible for rendering your web app, right? So it's stuff like the menus, the tabs, the window itself, all of the stuff that is the same no matter which page you're looking at. This bit of the browser is called the browser Chrome, which is not to be confused with the browser Chrome. Google named their browser after the browser Chrome because they are rubbish at naming things. Anyway, the other bit of the browser, which is the bit that renders the web page, is called the browser engine. And there's a few different engines floating around. So for instance, Firefox, which you may be familiar with, is an open source browser which runs on an open source engine called Gecko. Safari is a proprietary browser owned by Apple, and it runs on an open source engine called WebKit. Chrome, as previously mentioned, Google's browser, you might have heard of it. It's a proprietary browser, and it runs on an open source engine called Blink, which is named after a HTML tag because, again, Google don't come up with original names. I don't. So Blink is a fork of WebKit, and WebKit is actually a fork of an earlier engine called KHTML, which was developed for the Konqueror browser. If anyone here is familiar with KDE? Yeah. Then we have things like Chromium, which is an open source browser, which is also built on the open source Blink engine. And we can't forget Edge, as much as we might like to. Yeah, so Edge is built on an engine called Edge HTML because Microsoft are good at naming things. But as you may have heard in the news recently, they've actually switched out to using Blink. So this is what people mean when they say that Blink now runs on Chromium. That Edge now runs on Chromium. It's using the Blink engine. Outside of these major browsers, we also have a bunch of more, I guess, niche browsers. So things like Opera, which runs in embedded environments and low-powered devices. Samsung browser, which you might be surprised to learn runs on Samsung devices. The next one there is UC browser, which is in no way a niche browser. It's like one of the biggest browsers in China and India. And down the bottom is Brave, the privacy-focused browser. And all of these browsers, though, they all just run on Blink. So if your stuff works in Chrome, it probably works in most places. On desktops, anyway, and also on Android. On iOS, the situation is a little bit different. On iOS, everything runs on WebKit, because Apple has a policy that says browsers in the App Store have to be like web views on Safari, basically. But if you can get your stuff to work in Chrome and in Safari, there's a good chance it works everywhere. Now, whether you feel that's a good thing or not, I'll leave up to you to decide. Okay, so now we know what all the different browsers, all the different engines are. What do they actually do? And the answer is that they take HTML and they turn it into bitmaps that you can display on the screen. And they do that by taking your HTML, which arrives over the network as a stream of characters, and breaking it into chunks that the browser can deal with, which then builds a data structure that we can turn into a bitmap. And no, that is not a marquee element. I did that with CSS. So this process has essentially 5 steps. So tokenization and parsing happen every time a new document arrives over the network. We do that once. Layout, painting, and composite are known as the rendering pipeline, and these happen every time the screen refreshes. So 60 times a second kind of thing. If anything on the screen has changed, then the browser repaints it all. And it might have changed if you've resized the window or if some JavaScript has run and done something. All right, so let's start at the top. Tokenization. So tokenization is the process of taking that stream of characters and breaking it up into pieces that the engine can understand. So it's kind of like if you're listening to someone talk, what your ears receive is just a stream of sounds, but what your brain does is break them up into words that then you can use to construct sentences, if you can get them out. So HTML doesn't have words, it has HTML tokens. And if you've ever written any HTML, you're probably familiar with these. And if you haven't written any HTML, welcome. This is an interesting way to start. So we have start tags, things like an H1. They can have attributes on them, or they can be self-closing tags, which means they don't have any content inside them. We have end tags, which is the closing tags for those things. Text, which is the content inside those things. And things like comments. And there's a few other ones, but these ones are kind of the main ones. All right, so how does a browser do this tokenization? It uses something called a finite state machine. If you're not familiar with finite state machines, they have 2 parts. So we have the input, which is our stream of characters, and then we have a collection of states. And each state has some rules about what you should do if you're in that state, and given this current input character, what action you should take, and then which state you should go to next. All right, so let's have a look at that in action. So here we have a browser. Across the top, we've got our input HTML, and then we've got all the possible states. We start in the data state, and if we look at the data state, it's got some rules. It says if the current input character is a less than sign, then we should go to the tag open state. Otherwise, we should just omit the character and go back to the same state. So our current input is a less than sign. So let's do that. So now we're in the tag open state. Pretty exciting, right? Yeah. So the tag open state has a couple of rules. The first one says that if the current input character, now you might call this a /. The spec calls it a solidus. So don't know why. So if we have one of those, we can create an end tag token and go to the end tag open state. Otherwise, if we've got a letter, then we want to create a start tag token. We want to give it a name, and that name is going to be the current input character. And then we want to go to the tag name state. So we have a letter L there, so we will do that second thing. So now we have our token, it's a start tag token, and it has a name of L. And now we're in the tag name state. So this one, the default option down the bottom is the one that we're going to do, which is update the name to add the current character, and then go back to that same state. So we're going to do that as long as there's a alphabetic character, we're just going to add to the name there. Then when we get a space, we are going to go to the before attribute name. And then we're going to go through that same kind of process again to build up our attribute, the attribute name and the attribute value. And then when we get to the greater than sign, we're going to emit the token. So now we've got a start tag token and we can create the next token, which is a character token. So we can go through all of our HTML there and create tokens out of all of our characters. And then we've got our end tag token. And finally, we have another start tag, which is an input tag. And input tags are self-closing tags, so it's got no content. We give it our ID. And then we're done. So now we have a bunch of tokens. What are we going to do with them next? So the next step in the process is HTML parsing. And this is the process of turning our stack of tokens into the document object model, which is a tree structure that the browser uses to keep track of your HTML. It's sort of the beginning of the structure that we use to create our bitmap. So we're going to parse this document. It's a pretty straightforward HTML document. And the way that's going to happen is it's going to get passed to the tokenizer. The tokenizer is going to break it into tokens, and then it's going to pass it to the parser. So in the real world, as soon as a token is emitted from the tokenizer, it goes straight to the parser. So the two things happen kind of in parallel for performance reasons. Cool. So on that side is our input. And on the other side is the output, which is going to be our document object model. So we start with our first token. It is a doc type token, which was previously not mentioned. So this is a new type of token. A doc type token is a special token that tells the parser how to behave. Because a few years back, somebody had the bright idea that we should make HTML more XML-y, because we like XML, I don't know. So we wanted to make HTML so that it followed the strict rules of XML and it was more regular. And I guess it makes it a bit easier for the parser. So we needed to have this doc type token to say, hey, parser, this is an HTML4 document, you need to treat it more like XML. Then sometime after that, we realized that that maybe wasn't a great idea. And we'd actually just like to write HTML the way we always wrote HTML. Because the nice thing about HTML is that like half of the spec is just how to deal with things when people don't write valid HTML. So you can be sure, even if you don't write valid HTML, it will probably work. And people like that. All right, so let's just stick our doc type token into our output tree there. Next up, we have an HTML open tag. So we can stick that in our tree. And because we're building a tree structure, we need to keep track of what the current parent node is. So because this is an open tag, it's going to have children. So we need to keep track of that. So we'll put it on a pile down the bottom here, which is our open tag stack. All right, then our next open tag is a head tag. So we know that the current open tag on the stack is the HTML tag. So we're going to add the head tag as a child of the HTML tag. And because that's also an open tag, it goes on the stack. Then we have a link tag, which we can add as a child of the head tag. And that's a self-closing tag, so it doesn't need to go on the stack. Then we have our first end tag, and it's the end tag for the head, so we don't need to add anything to the tree. We just remove the tag from the stack. Cool. So now we've got a body tag, and because we've removed the head tag, the HTML is now the parent node, so we add the body as a child of the HTML tag. And then we can just keep going along, adding tags to the tree and also to the open tag stack. Eventually we get to some character tokens, so they just get added, they don't go on the stack. And they all get added there. Now in the real world, you add all of your text tokens together and your character tokens together, and they make a single text node. It turns out I'm not good enough at CSS to do that, though. So just imagine it. All right, and now we've got some end tags. We've got another open tag, an image tag, which is a self-closing tag, so it doesn't need to go on the stack. And then we've just got all of our end tags, so we can clear up our stack. And there we have our document object model. Yay! We're not quite ready to paint it yet, though, because first of all, we have to look at everybody's favorite language, CSS. So CSS tokenization and parsing happens at a couple of points in an HTML document. So if the HTML parser runs into a link tag, a style tag, or an element with a style attribute on it, then it's going to pass control to the CSS tokenizer and parser, and that process is going to run, and then we come back to parsing our HTML document. CSS tokenization is also a finite state machine. It's also specified in the spec as a finite state machine. I cannot understand how that finite state machine works, but it works essentially along the same lines as the HTML one. It's just not written as clearly, I think. So we're not going to go through that process. Then we also have CSS parsing, which again works a lot like the HTML parser, and the output again is the CSS object model. The CSS object model is a little bit more complicated than the document object model, though. And the reason for this is that when we create our CSS rules, we need to have a bunch of information that lets us work out which elements they apply to. And also, if we have two rules which change the same property on the same element, we need to work out which rule is going to win, right? So if we've got two rules that change the background color of the same element to blue or red, we need to work out if that element needs to be blue or red. So we end up with a much more complicated data structure, which has a bunch of stuff going on in it. So first of all, we need to track where this style came from. So it could have come from the user, the author, or the user agent. Now the user agent, confusingly enough, is the browser. So this is just the default browser styles. The author refers to you as the builder of the web page, and any style that you write that conflicts with a user agent style, your style is going to win. And finally, we have user styles. So users can actually create their own style sheets, which they can then apply to any page that they look at. It's not really a thing in browsers these days, but it used to be big. In the early days of the web, this was super important. I think Firefox still lets you do it. But anyway, any user styles are going to overwrite any author styles or any user agent styles. Cool. So then we have the selector, which tells us which element that this rule applies to. We have the actual property that we're changing and the value that we're changing it to. And we have these last two columns, the specificity and order. So specificity refers to like the strength of the rule, or the selector. So if you've got a selector that has an ID in it, that's going to beat a selector that has a class in it, and a selector that has a class in it is going to beat one that has just an element name in it. If you have a selector that has bang important on it, it's going to beat everything. So that might feel like you're winning, but you're not. And it probably means you need to look back at how you've built your CSS, because important can't be overridden with something more specific. So it sort of breaks the cascade a bit there. Finally, we have the order. And this literally is the order that these things appear in the style sheet. So this is like the ultimate tiebreaker. If we have a rule that applies, two rules that apply to the same property of the same element and they have the same specificity, the one that's in the style sheet last wins. So this table I actually stole from an article called Braces to Pixels on a list apart. The URL is down the bottom there. It's part of a series that goes into like all of the nitty-gritty of CSS parsing and tokenization and how this data structure is built. So if you're really interested in this stuff, I highly recommend you check out that article. All right, cool. So now we've got our HTML and our CSS, and with our powers combined, we can create a bitmap. Yeah, so we're going to start with our HTML, our CSS. We're going to apply all of our styles, work out where they go, stick them all in our style sheet there. And then we are ready to do some layout. So layout, as the name suggests, is working out where on the page everything is going to appear. So how much space everything takes up. So we're going to go through that. We've got our input tree here, and we're going to draw our layout on the other side. So we start at the top with our doc type node. This doesn't affect layout in any way whatsoever, so forget about it. So it's been a pretty easy start. Then we have our HTML element. Now this doesn't have any styling on it, so it's going to go in the output, but it's not going to take up any space. Next we have our head element, which has a special property on it called display none. And display none means don't put me in the layout tree. So we won't put that in the layout tree. We won't put any of its children in the layout tree. But yeah, if you are playing around with HTML, you can totally set the head element to be display block, and then you can see what's in your head element if that ever tickles your fancy. It can be handy for like doing talks where you want to show what's on. Yeah, maybe that's not a thing that everybody does. I don't All right, then we have our body element, and it's got a margin of 8 pixels. So if we put that in our layout, the body element itself doesn't take up any space, but it forces the HTML element to be bigger to account for its margins. Then our article element, it's got some padding and a background. We don't really care about the background at this point, but we do care about the padding. So we'll stick that on, it's got its padding, and then it's going to force the body element to be bigger, which is going to cause the HTML element to be bigger as well. Then our heading element, again, it's got some margins. And our single text node that my CSS couldn't handle. So we'll add them all. And you can see here that this text node doesn't fit inside the HTML element. So once we've got all of that content in there, we'll force the head one element to get bigger, and that will force all of its parents to get bigger as well. And finally, the image, which again doesn't fit, so everything gets forced bigger. So this layout process is basically put in something, put in its children. If the children don't fit, then make the parent bigger. And if that means that the parent doesn't fit in its parent, make that parent bigger. And we just go through the whole process until we've got everything on the page. So there's our layout. Now we're up to painting, which is finally getting to the fun bit, right? So painting happens in a very specific order. And this is where we're creating the actual bitmap. So we start from the bottom layer and go upwards, and for each element, we paint the background of the element, then we paint the borders of the element, and then finally we paint its content. So here's our page with our layout, ready to be painted. So we start from the bottom, which is the HTML element, and it doesn't have any styles on it, so we don't do anything. Next, we go to the body element, and let's imagine we put a class in our body element that gave it a beautiful gradient background, because gradients are cool. So we paint that. Then our body element doesn't have any borders, so we can go to the content. So the first child is the article element. So the article element, let's say, has a semi-transparent white background. So we'll paint that. And at this point you can see why it's important that we paint from the bottom up. Because if we've got something transparent, or if we've got something that's moved out of the normal flow with like a transform or a translate, they're the same thing, then you need to be able to see that lower element through it. Then we can add some borders to our article. And again, the reason that we need to paint the borders after the background is that the borders can be transparent. So it's possible that you can see the background through them. All right, then we had our text element, which doesn't have any borders or background, so we don't have to worry about that. We've got our content, which we can just paint there. Finally, our image element, which has no background, has a blue border. So we've got that there. And finally, the bit I'm sure we've all been waiting for, the content. Taco cat. Great, so at this point, we have a page, right? This could be sent to the graphics card or however that happens and painted on the screen. But there is still actually a step in our pipeline. And that final step is the composite step. And if you've ever worked with graphics software, you might have built an image out of different layers, right? So this is what the composite step is about, when you've got different layers, combining them together. So our paint step could potentially have produced multiple bitmaps, which we then need to stick together. There's a couple of reasons this might happen. So any knitters or crocheters in the audience would be familiar with Ravelry. Hi, Lily. So Ravelry, apart from being an excellent website, the search page is made up of 2 layers. So the bit outlined in purple at the top there, the header, is a layer, and the rest of the page is a layer. And the reason for this, you can see in the dev tools on the side there, is the position fixed. So if you've got something with the position of fixed, it means that it's been taken out of the normal layout flow and needs to be positioned independently of the rest of the page. So it needs to be on a different layer. This will also happen if you've got like transitions, transforms, floats, I think. Like anything that takes your element out of the normal flow is going to end up in a different layer. Yeah, so once we've done that, we've put all the layers together, we've got our page, it's ready to go. That's pretty much the whole process. So things to remember is that browsers are made up of a browser Chrome and a browser engine, not the browser Chrome, the browser Chrome. And those 2 are separate things and can be interchangeable. When your page arrives in your browser, it's going to go through tokenization and parsing, and then every time the screen refreshes, you're going to go through the layout, paint, and composite steps. And that, I mean, I didn't mention JavaScript, but that's a whole other topic. That's pretty much it. Thank you.
Thank you very much, Erin. Erin requested at the beginning not to have any questions, but of course you can intercept her and chat with her anytime you want. In PyCon's name, I want to give you this mug.
Thank you.
Thank you so much. And thanks again. Give a hand to
Cheers.
Erin.